how's everyone feeling today?
Totally awesome, sir.
All right, that's what I like to hear. So today's question is, how can we calculate the electrostatic force, or the magnitude of the electrostatic force between two charges? How can the magnitude of the electrostatic force between two charges be calculated? And the French physicist Charles Coulomb was the first to actually, identify and confirm this hidden relationship. And it was very, very tedious, and it wasn't an easy job to do. But he was actually able to calculate this force. And surprisingly, this force, or the formula to calculate this force, looks eerily similar to the gravitational force that Newton proposed. But yet this is a completely different force. This is not the force of gravity, it's an electrostatic force. Charles Coulomb, he was so cool. Charles Coulomb stated that if you have one charge, say Q1, and let's say it is a positive charge, and you have a second charge, Q2. Q is the symbol for charge. We've already established that light charges repel. And it's a third law action-reaction pair. We know that Q2 is going to push Q1 over to the left, and Q1 is going to push Q2 over to the right. Now, even if the magnitude of Q1 is different than the magnitude of Q2, they both experience the same force. However hard Q1 pushes on Q2, that's exactly how hard Q2 pushes back on Q1. So notice there's not like an F1 or an F2. Sometimes the problem will simply ask you, hey, how much force acts on charge Q2? But it would be the same answer if they asked how much force acts on charge 1. The magnitude of the force is the same because it's a third law action-reaction pair. And Coulomb realized that as well as knowing how much charge you have, Q1, and how much Q2 is, the other thing you need to know is the distance between the two. Sometimes this distance is called D, other times it's called R. You want to be comfortable whichever way that distance is denoted. I'm going to call it R. And Coulombs law simply states, if you want to calculate the magnitude of this force, the magnitude of this force is equal to the proportionality constant K, which has nothing to do with the spring constant. It's a completely different use of the letter K. It's called the electrostatic constant. Times Q1 times Q2 over the distance between them, R squared. Now the units of K dictate what the units of Q1 and Q2 and R has to be. So K happens to be equal to 9.11 times 10 to the 9th Newton meter squared over Coulomb squared. And since the electrostatic constant K is in newtons times meter squared over Coulomb squared, when you use this formula, the charge has to be in coulombs, and the distance between the charges has to be in meters, so that the coulombs cancel out and the meters cancel out, and you're left with newtons equals newtons. Now, a lot of times, we're just going to be focusing on the charge acting on Q2. And if we just focus on, the force acting on Q2. So if we just focus on the force acting on Q2, it becomes a scenario like this, where you have Q1, and then you go out a certain displacement vector, R, and over here you have Q2, and we know that like charges repel, so there's going to be a repelling force pushing Q2 away. And this repelling force is a vector quantity as well. And the official formula is that this electrostatic force of repulsion pushing it to the right is equal to K times Q1 times Q2 over R squared, where R is the magnitude of vector R. And the direction of this force is going to be in the same direction as this vector R right here. So times a unit vector R, where this doesn't change the magnitude, this just tells you the direction of the force. This just tells you the direction of the force is going to be the same as the direction as that unit vector R. Now notice though, if Q2 was negative, then it would be an attracting force, and the force would be to the left, so then it would come out negative times unit vector R, and it would be in the opposite direction. So this formula still works when one or both of the charges are negative. So this here is just a unit vector, and this is like fancy-dancy stuff. We don't normally even write that, but this is the official way of writing it, to say that the direction of the force is going to be in the direction of that R vector as long as Q1 and Q2 are both positive. Now you might recall with the gravity formula, the force was attractive when you had two masses. So there was a negative sign in front of that. So let's just take a moment and recall. This is a little blast from the past. If you had M1 and you came out a certain vector R away from M1 to M2, we know there would be an attracting force acting on M2. So this would be vector FG right here. And the magnitude of Fg, which is what we're interested in 9 times out of 10, the magnitude of Fg was just big G times m1 times m2 all over the magnitude of r squared. But if we wanted to write this formula out officially, vector Fg with its magnitude and direction is equal to negative big G times m1 times m2 over r squared times unit vector r. Remember, unit vector r is just a little baby unit vector that's in the same direction as vector r, but it only has a magnitude of 1. You know, the magnitude of unit vector r is 1. All unit vectors have a magnitude of 1. So the force due to gravity has that negative sign because when r is positive, Fg is in the opposite direction. But notice we don't have that scenario when we're dealing with the electrostatic force. If you have two charges, if r is positive, the force here is positive, as long as both charges are positive, by the way. And again, this unit vector r is just a baby unit in the direction of vector r. And the magnitude of unit vector r is 1. So you can see there's this huge similarity between Coulomb's electrostatic force and Newton's gravitational force. So the question is, like, which force is stronger? So I want to show you a little scenario. So let me open up this little PowerPoint that'll help you memorize this. The big showdown between the electrostatic force and the gravitational force. And the question is, which one has a greater magnitude? Which one has superior strength relative to the other one? Which one is the stronger force and which one is the weaker force? So before we actually see the showdown, does anyone want to place their bet? Noah?
I think it's going to be the electrostatic force because the constant is larger than the gravitational force constant, like it's to a positive power as opposed to like to a negative power.
Okay, so Noah says electrostatic force because he's looking at the constants. And the K value is much, much bigger than the G value. Okay, Sonny?
It depends.
You're going to say it depends. Okay? So,
On what? I agree.
you want to elaborate there?
Sure. If the gravitational, the mass of an object can accumulate to really, really huge, but I'm not sure if the overall charge of an object can accumulate to that big. And when you place it in universal scale, the gravitational force definitely plays a bigger role.
All right.
Yeah.
Let's see.
The tiny objects.
When you're comparing apples with apples, let's see what happens here.
Yeah, that sounds about right.
That was worth it. Get demolished.
Now, Sonny, I understand what you're saying. Like, if you have two neutral objects, the electrostatic force is going to be 0, and you could have a tremendous amount of mass, so the gravitational force would be greater. So you actually make a valid point here. But what we're going to do in the near future is we're going to place a proton next to an electron. And when we place the proton next to the electron, and we compare, because they both have mass, and they both have charge. And when we compare the force of gravity that's attracting them to the electrostatic force that's attracting them, we'll see that there is no contest. It really would be more like this, guys. You know, the gravitational force doesn't even have a chance. I mean, I hate to show this because it's ugly, but really, if there was a showdown between the electrostatic force and the force of gravity, okay, the electrostatic force would just squash the force of gravity.
David versus
David versus Thomas. Is that right?
So, we know that Coulombs Law states that F equals K Q1 times Q2 over the distance between them squared. And the K constant is 9 times 10 to the 9th Newton meters squared over Coulomb squared. And remember, we talked about how a Coulomb is a very large gang of elementary charges. Remember, it's 6.25 times 10 to the 18th elementary charges, yes? Well, in a simple hydrogen atom, you have one electron that's orbiting one proton. And there is an electrostatic force of attraction, and there's also a gravitational force of attraction. So your mission is to calculate the magnitude of both of those. Now, you're going to have to remember the charge of an electron is -1 elementary charge. And the charge of a proton is +1 elementary charge. But when you go to use that formula, guess what you're going to have to convert those elementary charges to? To coulombs. Okay. And then, of course, to calculate the force due to gravity, you're going to need to know the mass of an electron and the mass of a proton. So you could either Google it on your phone or you could look it up in your textbook, but you're going to need those values as well. So take a moment and calculate these two forces. All right.
Oh wait, no, that's gravity.
Wait, what did you get for gravity?
I got 3.61 times 10 to the negative 47.
So for the force of gravity,
Did I seriously put the distance wrong?
Yeah, that looks better.
Go.
the magnitude of the force is 3.61 times 10 to the negative 47th newtons. Now I should have probably rounded that to 2 sig figs because the distance given was only 2 sig figs. So a little bit sloppiness with my sig figs. So that's kind of a small force, 10 to the negative 47th. What about the electrostatic force? Did anyone get an answer? To the negative what?
I think he squared the electrons. I think he. Yeah, you made it negative squared when it should only be 1.
Oh, okay. Let's find the magnitude.
Because they're opposite charges. I think magnitude should have a sign.
Yeah, last time we did have
It's not
the gravity.
Now that negative sign just indicates that it's an attractive force and the force is in the opposite direction of the displacement vector. And remember, officially with the gravity formula, it's supposed to be negative big G m1 m2 over d squared. So the answer would come out negative as well if you weren't just focusing on the magnitude. So today's lesson, of course, is on Coulumbs Law that's used to calculate the electrostatic force between two charges. But finally, sometimes you'll be given like more than two charges. What's a poor physicist can do then? Say you have a charge Q1 equal to 6.7 microcoulombs. And remember, a micro means 10 to the negative 6. So that would be 6.7 times 10 to the negative 6 coulombs. And then down here, you have a negative charge, Q2, equal to 5.7, or negative 5.7 microcoulombs. Let's just finish this out, folks. And then if I came over here, let's say I had a Q3, and Q3 was negative 4.9 microcoulombs. And let's say I knew the distance between here and here was 0.12 meters, and the distance between here and here was 0.17 meters. If you wanted to calculate the total electrostatic force acting on this Q1 right here, the formula only does two charges at a time. So the formula F equals K Q1 times Q2 over R squared only handles two at a time. So what's a poor physicist to do?
Sum it up.
What was the different vector?
You could either do it
One is
twice or you would have to.
Vector.
Yeah, you have to find the resultant of the two vectors. You have to use the formula once and figure out how much force of attraction is going this way. And then you have to use the formula second time and figure out how much force of attraction is going that way. And then what would you have to do with those two forces? Find the resultant by putting them in head to tail form using pi tag. All right, have a great day, everyone.